In this video, I'm going to talk about the impact of D and R a little bit more. D being the common difference for an arithmetic sequence, and R being the common ratio for a geometric sequence. I'm going to talk a little bit about diverging and converging sequences when it comes to geometric sequences. We're going to touch a little bit on calculus, a little bit about limits, and then at the end I'm going to do a few examples of geometric sequences. So quick recap here. We know that arithmetic sequences are sequences where we start with a number and then we add a common difference, a constant number, all the way along to get our next elements of the sequence. And the general term is given by un equals u1, the first term, plus d onto n minus 1. Okay, so that's arithmetic sequences. And we also have geometric sequences. And with geometric sequences, we are multiplying by a common ratio, r. So here we multiply by r, here we multiply by r. It's the same number all the way through, and here our general term u sub n is u sub 1, the first one, times r to the n minus 1. Okay, and notice the similarity between the two formulas. They both start with a u1. With arithmetic, then we're adding on something. With geometric, we're multiplying on something. With the arithmetic, we're adding on d times n minus 1. And with geometric, we're multiplying on r to the exponent of n minus 1. Okay, so there's a lot of parallels there in the formulas. Let's take an example. Let's suppose we have 50, 55, 60, 65, and so on, and we're asked to find the general term un. So the first thing that I notice here is that we're increasing by the same amount each time. We're adding 5 each time. And as soon as I notice that, I know that it's an arithmetic sequence. So I can write it out this way. And I look, what's the first term? Well, it's 50. What's the common difference? Well, it's 5. N, of course, is the term number. So there we have it. Some people might like to simplify this. They go one step further and they say, oh, well, this is 50 plus 5n minus 5. So this is 5n plus 45. Then it looks a little bit more like the way we would put a polynomial. We could see this as a slope. We could see this as a y-intercept, right? So if we wanted to see how this sequence is behaving, we could see it as having an intercept of 45, a slope of 5. And so our first term here is 50, because of course we start with n equals 1, and off we go. Okay, so we can make that connection between a line and the sequence itself. And this is good to keep in mind because we're going to see shortly that we can also make a connection between a geometric sequence and an exponential or a logarithmic. And I touched on this just briefly in the last video. Okay, notice also that d is greater than 0, right? This d right here. And so because it's greater than 0, that means we are increasing. Okay, we're going up each time. Obviously, we're going up each time. We're adding 5, but you can also see it in terms of the slope. The slope is positive. So when a slope is positive, it means that we're increasing. Okay, there's that connection. In fact, d is the slope of a line that matches the arithmetic sequence. Okay, let's take another quick example here. Let's suppose we have 50, 45, 40, 35, and so on. What's going on here? Well, it's obviously an arithmetic sequence again. What are we adding each time? We're adding negative 5. Okay, we're adding negative 5, and so our d value is negative 5. And so our general term looks like this. The first term plus negative 5 onto n minus 1. If you prefer, you could write this as 50 minus 5 onto n minus 1. Okay, some people will stop there because that has the form of the of the arithmetic sequence. Other people will say, you know what, I want to go a little bit further. I want to write this as negative 5n plus 55 so that I can see the connection to a line. That is, we have y-intercept of 55. Our first term here is at 50, and we go down with a slope of negative 5. Again, our slope is equal to the value of d. Okay, and we can see once again that because d is less than 0, we are decreasing. That's obvious just looking at the sequence. When it's less than 0, we're decreasing because it's negative, but you can also see it in terms of the slope. The slope is negative, that means we're decreasing. Okay, now let's take a look here at another sequence. This one's going to go 3, 6, 12, 24, and so on. And you think, well, what's going on? Obviously, we're not adding 3 each time. Like I'm looking here at the first two, and I'm immediately subtracting them, seeing 3, and checking, does it work? No. Then the first thing I'm doing after that is I'm dividing them, and I'm seeing, oh, okay, it doubled. Does that work each time? 6 times 2, 12, yes. 12 times 2, 24, yes. Okay, so it's geometric, and r is 2. Okay, we're multiplying by 2 each time. All right, great. So the general term here would be un equals u1 times r, which is 2. I'll just put the 2 in right away. Might as well put the 3 in right away for u1 to the exponent n minus 1. Okay, so now we have a formula. I could find the 10th term of this sequence just by substituting 10 in there, or whatever I need to do. I've got the general term. Now, what I want to say here is notice that if I put in a big N, this is going to be a huge number. And the bigger N gets, the bigger my term value is. That is to say, there is no maximum value that UN can be. Okay? And we can actually see this in Desmos. So if I move over here, hope this works. Okay. So if I move over to Desmos here, and I take a look at this sequence, I can plug in a value of 1, and I get 3 times 2 to the 0 is 3. I get this point here, so my first term is 3. You can see it just like that. I could plug in a 2, it calculates to 6. I could plug in a 3, it evaluates to 12. Plug in 4, it evaluates to 24. And you can see, if I put in 5, there it is at 48. You can see that we have accelerating growth. We have what we call geometric growth, which is identical to exponential growth. Okay, and if I take this here, we can see that that's what's going on. We've got exponential growth. It's just that we only have points. We don't have an entire line. Now, because the value of un is getting bigger and bigger and bigger as n gets bigger and bigger and bigger, we can write that the limit as n gets bigger and bigger and bigger, as n increases towards infinity, of un, of the value of this, is in fact infinity. Okay, this is how we express in mathematical notation that un is growing without bound. There is no maximum. There's no boundary on how big it can get. It keeps getting bigger and bigger and bigger. Okay? And we also say that this sequence is diverging. Diverging basically means that it's not getting closer and closer to a specific number. So a sequence is diverging if it grows without bound, like this case here. If it grows without bound in the negative direction, in other words, if this was a negative infinity, we would also say that it's diverging. And the other way that a sequence can diverge is if, in fact, it doesn't get closer to anything at all. And we'll get an example of that coming up soon. Okay, so that's key vocabulary. The sequence is diverging. This is a key statement showing you how you can express that it's getting bigger and bigger without bound. And there we are with that sequence. Okay, now let's take a look at another one. Let's take a look at this geometric sequence here. I'm going to start with 3 again. And then I'm going to have 3 halves, and then I'm going to have 3 quarters, then I'm going to have 3/8, and it's going to go on. I want to find the general term. Okay, so my general term, again, is the first term times the common ratio to the exponent of n minus 1. What's the common ratio here? Well, it's a half. 3 times a half is 3 over 2. 3 over 2 times a half is 3/4. And if you couldn't pick that out right away, don't fret. You can just take the second term divided by the first term, and that will give you your value of r, if it is a geometric sequence. So 3 halves divided by 3 over 1, keep change flip, that's going to give me 3 halves times 1/3. The 3's cancel, so to speak, we get an r of a half. Okay. And I could check it, I could times a half by 3 halves to get 3/4, make sure that it's all good. Okay, so there's our general term. Now, this time, look what's happening. So here we are in Desmos, and I've actually just typed in on the left the sequences itself, and I've substituted in 1 for the first term, and here it is. It's a green dot. All right, great. 1, U1 is equal to 3. Then I took the sequence and I substituted in 2. Here's the next one. Term 2 is right here. What does that work out to? Well, 1.5. Here's the third term. Here's the fourth term. Here's the fifth term. What's happening here? Well, it appears that as it's shrinking, it's getting closer and closer to 0. Where did we see this before? That's right, exponentials and logarithms. Right? This is a decay. This is an exponential decay. And we're getting closer and closer to a value of 0. And so we say that the limit here, as n goes to infinity, is 0, just like we did with exponential decay. And I've actually made a little, oh, it's not working. Well, there you have it. I made a little thing, but it's not working. But you can see we've got this exponential decay here. So coming back over, we would say that the limit as n goes to infinity of un this time is 0. And we would say that this sequence converges. Okay, it converges. In fact, you could say it converges to 0 if you like. But it's a converging sequence because as n gets bigger and bigger, un gets closer and closer to a specific value. Okay? Now, let's switch over to another kind of example. There are 4 basic cases here. We've got the case where r is greater than 1. We have the case where r is less than 1 but bigger than 0. Now we're going to do a case where r is less than -1. Okay, so let's take this example here. We have 3, -6, 12, -24, and so on. What's the common ratio here? Well, it's -6 divided by 3, -2. We're multiplying by -2 each time. What's our general term? Well, it's the first term times -2 to the exponent n minus 1. But look at what's happening. It's very unstable. We're not getting closer to any number at all, and we're not even getting closer to infinity or to negative infinity because the sign keeps switching. So this is an example of a divergent sequence because it doesn't get closer to anything at all. Take a look here. If I have, let me take these off. Oh, I don't have it here. Well, let's take a look at an example like this. Here again, I have a negative base. Okay, I took negative 1.2. That is less than negative 1. And here I have the point at 1. Okay, 1, if you substitute it in there, gives you a quarter. What's the next point? Well, at 2, we get negative 0.3. When n is 3, it's above the line. When n is 4, it's below, above, below, above, below, above, below, and so on. And if I zoom out, you'll see that as n increases, it just keeps flip-flopping back and forth and getting bigger and bigger. Okay, now it's way up to almost 400 and just continues to go back and forth. I'm going backwards now. It started off near 0, and as n increases, it just explodes. But it goes back and forth. So here we say that the limit does not exist. This is divergent because it doesn't settle on a specific value, but we say the limit as n goes to infinity of un does not exist. DNE, common abbreviation for does not exist. Okay? And what if we had a negative, but it was fractional? So I think I had an example there over in Desmos where it was negative a quarter. Okay, we'll take r equals negative a quarter. What happens there? Well, switching back over, we can see, I'll take this one off. If I have a general term of 3 times negative 1/4 to the n minus 1, zoom in, and let's put our first term. We get, what do we get? To the 0, 1, we should get 3. There it is. Okay. Now the second term, there it is, negative 3/4. Third term, there it is. Fourth term, there it is, there it is, there it is. So we can see we're going back and forth, positive, negative, positive, negative, positive, negative, positive, negative, all the way, because we're multiplying by a negative with each successive multiplication by r. And yet, we're getting closer and closer to 0. Okay? So this sequence is convergent, and it converges to 0. We would say that the limit in this scenario, let's say un equals 3 times negative 1/4 to the n minus 1, okay? That's the one we were just looking at. We would say that the limit as n goes to infinity of un equals 0. Okay? And notice, I mentioned this before when we were talking about limits. If you had, this is a sequence, so it's just individual points, okay? But if we had a function, which we could very easily create, that went back and forth like this, it could still have a limit of 0, okay? Even though it crosses the x-axis. It is false to say that if you have a limit, it means the graph never crosses the value that it has a limit with. You can cross, in fact, infinitely many times and still have that limit. The key is, are you getting closer and closer? Okay, so here we're getting closer and closer, and so we have a limit of 0. And so because we have a finite limit, we say that this sequence is converging. Now we have a couple of degenerate cases. So what if r equals 1? Then what's happening? Well, that just means that we're starting with some initial value, let's say 2, and we're multiplying by 1 each time. Well, if we're multiplying by 1 each time, we're not going anywhere, okay? So you could consider this to be a geometric sequence, but it's a degenerate case. A degenerate case meaning it's not very interesting. It's not really doing anything. We certainly don't need to use all the machinery of geometric sequences in order to describe what's going on here. You just say, look, it's always 2. There's nothing special. What about if r were -1? Well, that's another sort of degenerate case. Maybe it's slightly more interesting than just a list of 2's because we're alternating the signs. But other than that, there's nothing special going on. So we don't really consider that to be a geometric sequence either. Even though it is technically a geometric sequence, it's a degenerate case. We could very easily just describe it as, hey, look, we're changing the sign each time. What about r equals 0? Well, that one also is a degenerate case. Look, if r equals 0, we're going from 2 to 0, because you multiply by 0, and then we get zeros all the rest of the way. That's not very interesting either. Okay, so when r equals 1, -1, or 0, we don't really have anything special going on. But when r is greater than 1, we have a diverging sequence. And we have that our limit, as n goes to infinity, of un is infinity. Okay? When we have r, I'm leaving a little space here, less than -1, we also have a diverging sequence. And this time the limit as n goes to infinity, it does not exist because we get the behavior where each subsequent value changes sign and it gets bigger and bigger and bigger and explodes. And then we have in the middle here the range of r's between -1 and 1, and where r is not 0, because that's not very interesting. And these ones we call converging. And in these cases, the limit as n goes to infinity of un equals 0. All right, so we've touched on some properties of these sequences. We've touched a little bit on limits, a little bit about convergence, divergence. We've made some connections with calculus a little bit with the limits. We've made connections to exponentials and logs a little bit. You can see how these things start to come together. What I'm going to do now is I'm just going to go through 5 examples or so of applying geometric sequences to solve problems. And then that will be it. That will cover 1F, 1G, and 1H. Okay, so here come the examples now. Example number 1. Suppose we have this sequence, 40, 20, 10, and so on. And it says find R and U12. Okay, no problem. R is going to be 20 divided by 40. That's a half. In other words, we're multiplying by half each time. And so my general term is going to be the first one, 40 times a half to the n minus 1. And so then if I want to find U12, I just substitute that in. 1/2, 12 minus 1. And if I were going to put it in exact form, if I didn't have a calculator, I would leave it like that, because nobody is going to expect me to multiply a half times itself 11 times on an exam without a calculator. Or perhaps if you wanted to, you could go a little bit further and say, well, this is 1 to the 11 over 2 to the 11, so we have 40 over 2 to the 11. Maybe that's slightly nicer. And if we had a calculator, then we would pull that up, and I'll just do it quickly, see if I can get anything interesting. To the exponent of 11. It works out to approximately 0.0195 to 3 sig figs. Okay, so that's that one. Next, let's suppose we have this sequence: 7x, 14x squared, 21x cubed, and so on. And again, they say find r and u8. Okay, you don't need to be intimidated by the x's. They're just variables inside our equation. So r is 14x squared over 7x. Okay, and I encourage you never to be intimidated by your x's if you can help it. So we've got the second one divided by the first one. That simplifies to 2x. Okay, so is 14x squared times 2x 21x cubed? Yeah, it is. Okay, so I've got the common ratio. That's fine, 2x. And now let's get the general form. So I get the first one, 7x, times my common ratio. That's 2x to the exponent n minus 1. And so to get u8, which is what is asked for, I get 7x times 2x to the 8 minus 1. That simplifies to 7x times 2x to the 7. That's, well, this is 7x times 2 to the 7 times x to the 7. I end up with 7 times 2 to the 7, x to the 8. That's probably how you would write it. Well, that is how you would write it if you had no calculator. And if you had a calculator, you would just evaluate that part and put that in front. Now, 2 to the 7 actually isn't so bad. 2 times itself 7 times is 128. So you could actually go 128 times 7. Maybe that's not so bad for no calculator. What's that? 5, 14, 9, carry a 1, 7, 8. Yeah, probably actually with that, you'd be best off to go to the final step because 2 to the 7 isn't so bad. Okay. Next example. Let's suppose we have a geometric sequence. Okay, so suppose you have a geometric sequence. We're given that with u3, the third term, 40, and u12, the 12th term, 454.5. Okay, and when I made this question, I had to round off a little bit. So there's going to be a bit of rounding in our answer, just to warn you about that. And now suppose they say, find u15. Okay, so this is a classic question where they don't give you u1. There are a few ways to do these questions. Here's what I think is probably the easiest. You think, okay, you don't have to write this part out in green, but just to help you visualize, this is the situation. Okay, so you have term 1 missing, term 2 missing, term 3 is 40, then you have a bunch of other terms, and then you get to term 12, which is 454.5. Term 12, this is term 3, this is term 1. Okay, so probably the easiest way to do this type of question is you think, how many jumps are there from the first number I know all the way to the second number that I know? Okay, how many jumps from term 3 to term 12? Well, the number of jumps is just going to be term 12 minus term 3, 9 jumps. Okay, you can see that easily here. If you want to know how many jumps from term 1 to term 3, well, 1, 2. It's just 3 minus 1. Okay, so you just subtract the positions to see how many jumps there are. Now, for each jump, you're multiplying by r, right? So to get from 40 to 454.5, we're multiplying by the common ratio 9 times. In other words, 40 times r to the exponent of 9 equals 454.5. And once you've got that, you're away to the races. Okay? Because once you've got that, you just have an equation where you can solve for r. And then once you have r, you can set up your general form and you can find u15 and you can find anything else you want. Okay, so this is probably the easiest way to think about it. You just think, what's the first number? How many jumps? Which is just the places subtracted. That's 9. And you set up an equation. So here now I'll divide both sides by 40. I'm going to pull out my calculator, make this a little bit easier. I get 11.3625. Then I take the 9th root of both sides. Remember, you can take an indexed root. So I'm going to take the 9th root here. This is the same as 11.3625 to the exponent 1/9. Okay, that's how I would do it on my calculator. So I have my 11.3625. I go to the exponent, bracket, 1 divided by 9, bracket, equals. And here I get 1.31001. Okay, so that's 1.31 to the nearest 3 sig figs, or it's 1.31. As I say, when I made the question, I couldn't quite make it exact, so that's what I got. And so now we can get the general form. UN is the first term, 40 times 1.31 to the n minus 1, and we can evaluate for whatever we want. If we're asked for U15, we just substitute in 15 and plug it into a calculator, and away we go. We get something. Okay. Next question. And these are all different types of questions that are common in arithmetic and geometric sequences. Okay, the one where they don't give you the first term is a common type. This next one is a common type where we get a variable in our sequence. Okay, so here's the next one. It says if 8, x minus 5, 1/2 are the first 3 terms in a geometric sequence, find x. Okay? And once we find x, we could find r. And once we find r, we could find any term in this sequence, right? So finding x is just the first step to solving a whole bunch of different types of problems that could be asked of you here, okay? But I'm just going to solve for x, and then the rest I'm sure you can figure out. So if I want to find x, I'm told that it's a geometric sequence, so that means I know that 8 times r gives me x minus 5, and that x minus 5 times r gives me 1/2. Okay? In other words, x minus 5 over 8 gives me r, and 1/2 over x minus 5 gives me r. These are just the ratios of the terms. The second one divided by the first one is r, the third one divided by the second one is r. Okay, well, if both of those things are true, then both of those ratios have to be equal to each other. So I have x minus 5 over 8 equals 1/2 over x minus 5. And now I can solve for x. Okay, I'm going to multiply both sides by 8. I'm going to multiply both sides by x minus 5. As so. And now this comes back to quadratics. I can multiply this one out. Subtract 4 on both sides. Factor what two numbers multiply to negative 21 and add to negative 10. That's going to be a negative 3 and a negative 6. This is a positive 21. That's going to be a negative 3 and a negative 7. So I have x minus 3, x minus 7. So x equals 3 or 7. There we have it. Okay, and I could end right there because they just asked me for the value of x. But let's go one step further and just see what this looks like, just to get a bit of a deeper understanding. If if I copy my sequence here, the first three terms, and bring it down so I don't have to keep flipping back and forth, up and down, I'm going to substitute in the values of x. So my solution says, hey, there's two possibilities here. You could have x equals 3, you could have x equals 7. Well, in the case where x equals 3, what does that give me? Well, it says I have 8, 3 minus 5 is negative 2, positive a half. What's going on there? Well, my common ratio is negative 2 over 8. It's negative a quarter. Okay, so we've got a scenario where we're going to have a limit that gets un. The limit as n goes to infinity of un equals 0. And you can see that as, 8 in absolute value is the biggest, and negative 2 in absolute value is smaller, and a half in absolute value is even smaller, and we're getting closer and closer to 0. And you can also see that because this negative 1 quarter falls between negative 1 and 1. And whenever r falls between those two values, we have a converging sequence that goes to 0. Okay, that's interesting. The second one would be if x equals 7. What would happen there? Well, we'd have 8 first, of course. Then 7 minus 5 is 2, and then a half, and so on. Well, this is the other side of the same equation. Here we have r equals positive a quarter. Okay, and you can see how this is also going to converge to 0. We have almost the same sequence. The only difference is the first one is going to alternate the signs, and the second one is going to be all positive all the way. Okay, so if we were going to graph it, we would have the first one going like this, and we would have the second one going like this. Okay. Okay, last question. Let's suppose we have a town that has a population of 5,000 people in 2024. Okay, a town has a population of 5,000 in 2024. It is estimated that the population will shrink by 20% per year. Find the population in 2032. Okay, now we could have had an identical question in our exponential unit. In fact, we did have extremely similar questions in the exponentials unit. Here, we're just looking at it in terms of a geometric sequence. Okay, so our first term is 5,000. That's U1. Our second term is going to be whatever happens after this population decrease. But we have to think, what are we multiplying by to get a reduction by 20%? Well, that 100% population is being reduced by 20%. In other words, we end up with 80% of the population we had before, which is 0.80 or 0.8. My r is 0.8. All right, great. So I can set this up then. I have the nth term is the initial times 0.8 to the n minus 1. And the only thing here that I have to be careful with is which term number matches which year. Okay, so the first term matches 2024. Which term number matches 2032? Well, we can see it this way. If I have the first year is 2024, and the second one is 2025, and so on, and I'm going up to 2032, What's the difference between these? Well, the difference is always going to be 2023, right? 2024 minus 1, 2023. 2025 minus 2, 2023, okay? So if I want to know what term number I have, all I have to do is subtract off 2023, and I get, what do I get here? 7, 8, 9, okay? So it's term 9 that we're looking for. This little technique is really important because what if they said this continues all the way to 4117? You don't want to be writing out everything all the way up to 4117, okay? You want to say, okay, well, let's take the first term and see how much do we have to subtract off to get the term number, and then just apply that same constant to figure out the term number of, 4117. In fact, if they wanted us to do it, this is what we do. We'd be looking at term number 2094, okay? But for our problem, we're looking at term number 9, so I'm going to substitute a 9 right there. I have U9 is 5,000 times 0.8 to the 9 minus 1, and I can pull out a calculator here. Okay, this town is actually going to be decimated. You can see that 0.8 to the exponent of 8 on my calculator, 0.8 to the exponent of 8. Well, that's 0.16777. That's nasty. Times my 5,000. Okay, we're left with 839 people to 3 sig figs. 839 people are left in the town. All right. So this should give you enough now to work on exercises 1F, 1G, and 1H.